All right, I got a interesting little situation. Basically right here I have a TL072 op amp that got configured as a non-inverting amplifier with a gain of 3. Just straight up, you know, simple as can be. And I was kind of curious, because I have in mind an application, okay, where I've got like a anyway, I have an application where I'm gonna, I've got a DAC, okay, on like one of those ST microprocessors, the Nucleo kind of thing, you know what I mean? And but it's 500 kilosample DAC, and I'm just kind of wondering, because I need like an output for that, right? But I would like to amplify the 3 volt signal, ultimately up to like plus or minus, peak to peak of 20 volts, for example. And but I'm really trying to evaluate, various op amps with that in perspective. So, but it is a 500 kilosample DAC. In fact, it's actually got really two DACs on it, but one is split into two channels. So, they're 1 megasample DACs, but since you got to share one, and I want more than two channels, I'm gonna have to basically run them at 500 kilosample. um, so, but at any rate, I'm gonna need some kind of linear amplifier that faithfully reproduces the input signal. But that's got me to looking at it and thinking about crunching the numbers on it and stuff. To see what you're really gonna be left with here. So um, so basically, I went in and generated a whole host of different waveforms because I realized that see right now I got the output peak to peak at about 20 volts here, which you really can't see too clearly. That just take my word for it. It's about a 20 volt peak to peak. Um, you know, Gain is about 2.8. Um, so the frequency right now I got it set to 2.5 kilohertz. But I with a 500 kilosample DAC, the maximum actual frequency you could generate is about 250 kilohertz, and that assumes that you're outputting a high and then immediately a low and then a high again, etc. Um, and um, the interesting thing about this TL072 op amp is that it actually has a power bandwidth, of about, let's see, about 280 or so kilohertz. I'll show you. Go back to the basic. Yeah, 258 kilohertz. Oops, going the wrong way. Okay, so basically I got it set to a square wave. That's what a square wave looks like, and this is of course slew rate limited. It's a slew rate limited bandwidth, and again I got this set to a gain of 3. So at this frequency you're gonna have approximately like an open loop gain of like 12 or so. So so I've got a loop gain available of about 10, at this closed loop gain of 3. So, so you're still going to get, fairly linear behavior, etc. Um, at this level. Actually, I got it set to 250 kilohertz exactly right now. So, yeah, that's what I was setting for this test. Let me see. I'm going to make it exactly. Okay, so I got it set to exactly 250 kilohertz square wave, right? And that's what you're going to look at. That's the maximum output a DAC could actually generate, and that's going from, essentially 1 to 0 to 1 to 0, even though this actually waveform actually has a lot more points than that, but still it's slew rate limited. So, by putting a square wave into it, you're seeing what the maximum, you know, kind of signal rate coming out of a DAC could handle at a full power bandwidth, 20 volts peak to peak. So, this is the maximum signal you could generate out of a 500 kilosample DAC. And this is how this device would handle it. It doesn't look like a square wave, it looks more like a triangle wave, with flat tops and bottoms a little bit. But that's the best you could do, and that's going from, range to range. Now, of course, if I cut the voltage level down, it would look more and more square wave like. See, 3.375. Let me copy that before I make a change, just to show my point. So the more I reduce it, the more square wave like it looks, and we're down to about a 5.6 volt peak to peak at this point. But going back to my full power bandwidth, that's where we're looking at. That's the maximum signal you can generate, out of this particular DAC, and this is how this amplifier will respond to it. Again, it's quasi sine wave like, and and this is 5 times faster, if I'm not mistaken, than like a sound card on your computer would generate, in its DAC, generating your stereo output. So, of course, it wouldn't go over this. Usually it wouldn't go like 20 volts peak to peak, not coming out of your computer anyway. But the point is that this is actually a lot faster of a DAC, than you'd see in a sound card. But and we'll come back to that in a little bit. But going back to my custom waveforms over here, and let me go to the next logical level. Let's see, which is a 10 sample signal. That's about the best, crude little signal you can do. Is you got a signal like this and a signal like that, and so let's see. Let me go change the frequency here so we can see the whole thing. So yeah, we're at 20 volts peak, and we still got our gain of 2.9. So but like I said, that's the kind of signal you're stuck with. I'll try to put the camera down so it doesn't jitter around on you too much. But that's the kind of signal you're stuck with. And here's an alternative signal. This one I created directly, by entering the numbers. This one, was a sine wave that the program itself sort of generated, although I think it has noise in it. Let me go in and edit it, and I'll show you how this whole process works. Say I got it set to 10 seconds, and hey, you create your own waveform. You got to go here. The default samples is like 4096, so you got to go enter a number here first in the math, and then once you've entered that, click outside of it so that sets it in place. But that sets it for all these outputs once you set it there. A little silly, but and confusing, but that's how it works. But you can generate your own math function. In fact, the function I got here is actually this function that I just hit generate. Alright, that fills it in. But I'm going to go ahead and actually generate a sine wave so that it'll, without noise in it. So it'll be a little modified version of it. So supposedly that's a better sine wave representation. So at least without that noise signal, so the levels are a little more spread out now. But yeah, that's about the best you can do, and that's I really had to adjust the frequency up, because that you can do up to about 50 kilohertz. So this is what that same signal, again about a 20 volt peak to peak, would look like at if it were coming out of that DAC at a fixed frequency. fixed megasample rate of 500 kilosamples per second. Um, this is what it would look like, basically. So, you can see it's like aliased out the ass, it's like to borrow a term from graphics, they call it aliasing when you get jaggies in it, and you have anti-aliasing techniques you apply that, actually dither the line so it looks smoother. But, um, but yeah, you get this kind of jaggedy pattern here, and that's because you only got 10 samples per waveform, In fact, you can see over here what it actually looks like. So those are the 10 samples it's trying to generate. So, I mean, if you think about it, you got 5 samples for the positive side of the waveform and 5 samples for the negative side of the waveform. But that's like 2.5 samples or something, from zero to negative and from zero to positive. So, you really only get like vertical samples altogether. That's your vertical resolution. So, I mean, geez, that's, um, even a 4-bit DAC would give you 16, right? So, you know, it pretty sucks, but that's what it takes to get, that's the best you can do for a 50 kilohertz signal. You can't do any better than something like this. And I did, um, let's see, I don't know if I did it at 10 or not. Let me see. Yeah, I don't think I did it at 10. No, I did. Um, here is what, the smoothest waveform you can produce is like a ramp rate, and you can see the slew rate doing its thing here. That's why you have this little slope here that's not vertical. But, this is the smoothest you can do, using all those 10 samples from, you know, negative Vmax and positive Vmax. So that's as smooth of a waveform as you can make at 50 kilohertz with a 500 kilosample DAC. Now, of course, in a real DAC, what they'll do, and since the slew rate is one of the big limiting factors here, not the only one, but it's one of the biggest limiting factor here. Is that basically all these sharp transitions are happening at the same speed. They all would have the same slope if you were to actually measure it, and that's going from like here to here, for example, versus here to here. What they'll do is they'll put a low pass filter that's set to where anything above 500 kilohertz or so, in this case, would actually go through a low pass filter and be kind of filtered out. And it smooths it out a lot because a lot of these are really representing, higher frequency components, all right? But it's slew rate limited, and we saw the slew rate, is actually, the power bandwidth, is slew rate limited too to over 250 kilohertz. It actually is like 280 or so. You can generate still a pretty good looking triangle wave at 280 kilohertz, not half bad. 20 volts peak to peak. But anything above that, is certainly going to have harmonics. So, so therefore, like I said, we're at, 200 I said 250 kilohertz is the maximum, like we saw in the first sample. Um, on that other screen previously. Um, but you're going to have harmonics, at double that, and I think it's every odd harmonic or something like that. So, but again, generally speaking, if you filter it based on, about um, 500 kilohertz, no less than that, although you might be able to get away with less than that, but if you low pass filter it, because you're probably not going to generate a very fast transition like what I showed you in that other screen, um, very often. So, that other screen being, here, you're probably not going to do this very often, right? Because this is at a 250 kilohertz rate. Like I said, this is the maximum signal you can generate, and like I said, it is generally slew rate limited. But at any rate, because of that, like I said, you can actually filter certainly above 500 kilohertz at your corner frequency at that, and that'll get rid of most of that jagginess we are um, seeing over here. And that's how sound cards deal with it, even though usually they only have like 100 kilosample DAC, but they have appropriate output filtering, so if they may be dealing with really coarse signals, even though they have 16-bit DACs and shit, which means that certainly the lower the frequency, the more precise they'll get. But um, but they have decent filters in there that basically smooth a lot of this shit out. Because if you'd actually listen to this thing, it would be hashy. I'm surprised they don't have a way of listening to these waveforms. But the fact it's on a PC, because like I showed you in another video, the PC scope in this software allows you to actually do that. But here they don't seem to have that functionality. But well, maybe there is. I wonder what this is. Audio. Oh, eh, well, we're I guess too high of a frequency to hear. Um, now we'll play with that again here later. Where do my measurements go? Uh, Shit. Where do they go? Oh, oh, turned them off. But at any rate, but that's what it would look like at 10 samples, right? Because like I said, it's not all that great, but that gets you to 50 kilohertz. So, and this is 50 kilohertz signal, so I couldn't hear anything. I guess you could drive like ultrasonic transducers with it or something, but the next logical step is say, well, let's see what it looks like at 20 samples per second. Now, of course, by going to 20 samples a second, 25 kilohertz is the maximum frequency you can generate. Um, so, basically, this is what that would look like, but I gotta adjust the frequency down to 25 kilohertz, even though I don't have to. They all look the same no matter what. But at any rate, so you get a much better defined, in this case, sine wave. Um, they're still quite jaggy, but again, that can be filtered out with the same exact filter I was talking about before, because it's still all got the same slew rate. So, and it's this slew rate that's responsible for generating those harmonics. So it's really this transition that's doing it from one level to another. So, and the larger that transition, the higher the amplitude of those harmonics. But the harmonics are still all going to be kind of similar, because the slew rate's pretty much set in stone, even though slew rates and op amps do vary based on temperature and crap, but a little bit, but they're still all generally in a certain ballpark. So, so really, you can design a filter, a fixed filter, to take care of a lot of these things. It just filters out anything, again, certainly over 500 kilohertz, but maybe even less, and it depends on what order filter you make it. Even a first order filter would, help a lot, on something like this, let them go into a second or fourth order filter. But at any rate, the point is that you see much better resolution, although our maximum frequency is 25 kilohertz now, which you may not be able to hear. Now, I'm not going to go into some of the issues of, well, how would you generate 24 kilohertz, because I mean, I think I kind of did a video on that a while back, involving analog discovery and tricking this thing into generating a 50 megahertz waveform out of it, which it resists, but you can use these same techniques to do that. But it can be complicated. If I wanted to make it, instead of 25 kilohertz, like 24 kilohertz, you're going to really have to change your waveform equations every time you change the frequency, because it's going to change the wave shape a bit, because you still only have so many samples to work with. Right now we're working with 20 samples, so that doesn't give you a lot of variability if you're trying to make subtle changes in your frequency, but that's a different issue um, right now. The more samples you got to work with, the more easy it is to make adjustments like that. I mean, I could do a whole video on that topic alone, what your resolution limits are, at every given frequency, what's stable and what's not, for a given number of samples. So it gets complicated if you're trying to make subtle adjustments in frequency when you got a fixed sample rate. Um, so it helps if you can fine tune the actual sample clock rate, of your DAC, externally. If you can control that like linearly, okay, then you can generate any frequency at the same signal. But usually in a microprocessor, you got kind of a fixed frequency you're dealing with. You can't really move it, adjust it smoothly. So if you're working with resolution like this, your options are a lot more limited. The larger the number of samples, the more stable frequencies you can generate. So, but again, that's like a different subject. But I did a few different waveforms at this same sample rate. So this is what a stepped waveform would look like at this rate. And again, the slew rate at this frequency is still abundantly evident. But that's about as smooth as it gets. It's a definite stair-step waveform, still being roughly 20 volts peak to peak. But let's see, I think I did. No, I think this is the last 20 sample one I did. So the next step was to go, to get us some higher resolution, because still 20 steps just isn't a lot, like I've been discussing. But you can go up to 50 sample, but that drops your frequency down to, in my case, to 10 kilohertz. So, make that adjustment. Again, these all look the same. I really don't have to go adjust the frequency, but just for sake of completeness and for people to satiate people's curiosity. So this is what it generated, from a sine wave perspective. And again, at 50 samples, we got 50 samples on the positive side, 50 samples on the negative side, so that's about 25 vertical and 25 horizontal, or 50 total peak to peak. So that's still a pretty damn low, I mean, what is that, like a 6-bit DAC? So, that's what a 6-bit output waveform might look like, although it wouldn't look quite this smooth, because, this is higher than 6 bits. I mean, this is a 14-bit DAC. So, not all these voltage levels are equal, but if you look at a stair step, this is what a 16-bit DAC would look like here, or a 6-bit DAC would look like. But in any event, the point is we're a lot smoother now. You got more variability, but again, our maximum frequency is 10 kilohertz, and let's see if we can hear it. Maybe I got the volume turned off, or maybe it just doesn't work this way. Maybe output NVIDIA. Yeah, I don't know. I can't hear a damn thing. How to fuck with this for a minute. Okay, I got it to work. I had a dick with it, but apparently the maximum DAC rate of a sound card, at least this one, is 192 kilohertz, so that's interesting. But anyway, I guess that's what it sounds like. I mean, I find that hard to believe. Let me see if, okay, so you can kind of hear that. I don't know what all that clicking is. I don't know if that has anything to do with the aliasing, but sort of sounds like a signal. I don't know. Yeah, I don't know what the clicking is. That pretty much sucks. I don't know. Speed, what's that do? I have no idea. 10. What kind of speed is that? Okay. Anyway, but the point is, I guess they can do that for what it's worth. It's kind of annoying. But yeah, the only other signal I generated was this little, because apparently they have other signals, a few extra signal shapes in their editor that they don't have in the main deal. You got the rise, decay, and a Gaussian. That's what this is, a Gaussian. Let's see what that sounds like. Okay. But at any rate, that's again about the best you can do, and that's like a, you know, 10 kilohertz signal. Um, let's see. Now let's go up to 100 sample signal. So that's what a 100 sample signal looks like. But we got to adjust our frequency down to 5 kilohertz because that's going to be your maximum bandwidth with a 500 kilosample DAC. So let's see what that sounds like. Shit, I can hardly hear that. Anyway, I don't know. I think this needs some work because I guarantee you this frequency wouldn't sound that shitty. I mean, I can hardly hear a tone of any kind. Change the speed thing. Huh. Kind of hear something, sort of. I have no fucking idea what this thing's doing. Anyway, but yeah, so that's what 100, sample, would look like. And here's what our ramp wave would look like. Now, this is a very interesting feature, and this has to do with the op amp. You can see there's a slight curve to this. It's a little difficult for you to see with that stupid glare in it. But, there's a slight curve here. Unbelievable. But yeah, there is a slight curve here, and this is related to the slew rate on this particular op amp because this op amp actually generates like rounded corners and stuff instead of having the overshoot and shit. I haven't really seen much overshoot in this op amp, but what it does instead, it has some kind of a filter or something related to the slew rate. So if you have a hard slew rate transition from one point to another and then it transitioning out, it tends to create a little bit of distortion, and that's what you're actually seeing here. And that's what a sine wave looks like again at this. Oh well, that's 200. But that's the sine wave. And here, let's see. I'll go ahead and create a new one for you so you can see the process. See, that's what a what did I do? Edit it? God damn it. Here's a brand new one. So, I'll go set it to 100 samples per second. You click somewhere, and then I'll call it, 100S try. So I'll generate a triangle waveform. And that way, like I said, because you can go over to here, for example, and actually directly enter all the values of these manually if you want, which is practical to do if you're doing like 10 samples or something like that, or fewer. But let's go ahead and set it to triangle and hit generate and OK. Alright, now same number of samples, so it's 50 high, 50, 50 on this side and 50 on this side, so 50 peak to peak transition in our case here. But you don't see any kind of curves or anything. This is almost a pretty much perfect straight line. So, but that's because the slew rate, isn't having a big impact here, because the waveform itself is generally pretty gentle, even though it does have these little slew rate driven elements that are so small. Apparently, it's not enough to generate a big, like distortion, like you were seeing in that. In this here, because that definitely has distortion. It's got the same samples too, but the difference between these two waveforms is this big vertical, huge drop in slew rate. So this is how it's dealing with its desire to do an overshoot, because normally an op amp would probably overshoot in this situation, at all these transitions. So, these sharp transitions, like on a square wave. So, In fact, I guess we could do that too. Let me, I haven't actually done that yet. Let me make a new one. Same 100 sample, call it SQ for square wave. Alright, and 100. This isn't going to be too eventful. What's aggravating is they actually don't have a trapezoidal function here, so I can't really do a controlled, slew rate because of that. But anyway, go ahead and generate it and hit OK. Alright, so that's basically, you can see here we got a sharp vertical transition and then a curve here, and then another sharp transition and a curve here. These are distortion events that, because it's slew rate limited, we see these. If I go over and generate a trapezoid wave, here at, this is going to be a little disingenuous, but because it's going to be at full resolution. Let's see, go over to the basic, alright, and go down to trapezoid waveform, alright, and then drop it down to from 250 kilohertz to 5 kilohertz, what we're looking at right now. See, this is very, very good. There's a little bit of maybe curve or something going on here, but you can't really be sure what the cause of that. But otherwise, this looks about perfect. Like you'd expect at 5 kilohertz, but you don't really see, the kind of anomalies you did with that square wave we were working with. So, going back to our waveform over here, the next step though is to consider what 200 samples look like. So 200 samples, you got a really smooth waveform, but you're limited to 2.5 kilohertz. So that's about the best you can do. So let's see what that sounds like. A lot of crap. Yeah, that's bullshit. You can kind of hear a tone. Yeah, they need to work on this. But at any rate, like I said, that's giving you, again, 200 sample, a total of 100 vertical samples. But that's still less than what an 8-bit DAC would do. An 8-bit DAC would do 256 vertical samples. So, it just kind of puts things in perspective, that, that you can only do so much, even though you think, hey, 500 kilosample, that's high speed. Well, really, we're sitting here at 2.5 kilohertz and only just starting to actually have things, look, really, really smooth, almost like, that's 100 sample right there, and that's our other 100 sample. But, they're looking smooth enough to where, you almost don't need filtering, right? Even though there is definitely some high frequency harmonics that they're going to be really, really tiny. A simple filter would definitely correct that. But at any rate, it just goes to show you, that what the limitations of, of DACs are, and why, you really need pretty high frequency DACs, even if you want to generate audio signals directly, with no filtering. So, but otherwise, sound cards and so forth do use filters. They have usually digital because digital filters aren't going to do you any good there, because you really, this is a physical effect. This is more about the process of electronics. There's no computer code you can do, okay, that's going to turn this into a sine wave, or anything resembling a sine wave. So, you've got to use actual electronic filtering for it. But again, it's really a low pass filter, and just depends on how sharp your transition needs to be and what order you need to use, and that would require some experimentation. But I'd think a first or second order filter would work, would go a long ways in helping, depending on what you set your corner frequency to be. But the good thing is, I think it could be a fixed corner frequency in all likelihood. So, but anyway, it's pretty surprising that the stupid sound cards can actually do frequencies that high. So theoretically, anyway. I mean, we didn't hear much out of it though. But I mean, that's interesting. Their sample rates, output rates that high. But it doesn't surprise me that much. But it's interesting. Faster than I would have thought. So, hmm. But at any rate, makes you think. Using a sound card, as an output, might be a good idea for some things like that, because you could, especially, get one from an older PC, you can almost hack it. Um, because I do have several older sound cards lying around that probably have pretty high sample rates. You could almost hack one, with an Arduino or something, have an Arduino drive it. Um, although that might be a little slow, but my point is, I think it could be, definitely driven by a microprocessor, right? Um, and like I said, most of the sound cards at least 16-bit. So, this food for thought. You know what I mean? Um, I don't know about driving some of the new like PCI Express cards or anything, but um, anyway, you certainly need some modification if you wanted to do like DC level signals or anything approaching that. You might have some complications because of the filtering. But at any rate, I just wanted to kind of demonstrate, that yeah, even a TL072, actually could be used, for a 500 kilosample DAC. It's actually practical because most of the time your signals aren't going to change that much because it's not practical to generate more than, really a 25 or 50 kilohertz signal max, and that's if it's as crude as this. So, I mean, again, it's your options are kind of limited, is the whole point I'm trying to make. So it just helps having a video like this so you can actually put things in perspective if you're thinking about working with DACs. Um, as far as what kind of realistic frequencies you're going to get out of the thing and what kind of actual resolution you're going to be able to realize. Because again, the DAC I have is like a 12-bit DAC, and that means it can do 4096 levels. Really, I guess it can do all the levels this thing can do at maximum. So but at 4,000 you know levels, I mean, just to make a ramp wave, would require 4,000 signals. All right, 4,000 voltage levels. If you wanted to do a triangle wave from peak to peak, that would be 4,000 to rise and 4,000 to fall. So that would require 8,000 samples to fully take advantage of that resolution. 12-bit up, 12-bit down. For a full waveform. So, and that's if you go rail to rail, obviously, because that's another thing. Is that if you don't go as high, you usually lose resolution. But here the resolution's so low, I could actually make this signal a lot less than 20 volts peak to peak and not lose any resolution at all. I mean, because it's only, like I said, a couple of samples high or a couple of samples low, and even if we look at, a 50 sample signal here like this, we got like 12 up and 12 down. So, if you had a DAC, a 12-bit DAC, um, you would be using, and let's just let me get my calculator here. So if you had a 12-bit DAC, in a 20-volt signal range, 4096 samples, that's about 4.8 millivolts per sample. So, so if you could rise, like, let's say 13 samples, well, what did I say? Okay, we're at 50, so 25 samples across the board, okay, would be a minimum of 122. So I could take this thing to 122 millivolts, all right, and still have it look the same, with a 12-bit DAC. So I can make this signal a lot smaller, whereas, if I was pressing my DAC to the limits, I couldn't. Like if I had a 12-bit signal here, so if it looked like, um, if it looked like, this, okay, which is 14-bit level. Well, if I try reducing this signal size, you lose resolution because you're seeing, a full, you know, um, well, I don't know how many bits they're actually generating here. Let's assume 4096. Let's treat it like a 12-bit deal. But the fact of the matter is, if I shrink the signal size, you eventually start running out of resolution. As you start getting down to, because again, this thing will only put out a maximum of 5 volts divided by, say, 4096. So it's limited about 1.2 millivolts per step, theoretically. So, so with that being the case, I mean, if it's 14-bit, it'd be less than that. But and I think it is 14-bit because again, you can get down to um, it goes down to like microvolts, right? 500 microvolts per division and so forth. And let's see what this. Okay, your signal generator's amplitude is limited to 50 millivolts max. Let's see what that looks like. Well, never mind. Yeah. Okay, let's see what that looks like. And see, this is all kind of buried in hash and stuff. This thing probably does have some kind of filter, because it's got its own op amp in it, so it probably is filtered. But again, our resolution is severely limited by, you know, by that fact. Let me cut it down to 10 millivolts if I can. Nah, it won't let me go below 50. So at any rate, yeah, that's about the minimum signal this can generate. I don't know what its actual resolution is. I mean, it looks on the surface pretty good, but whether it actually is or not, I got no clue. Oh, come on, damn it. Seriously? What a piece of shit. Yeah, can't adjust it to stabilize it. Guess this stupid, there we go, you piece of crap. But yeah, so, again, I really can't see any jagginess, but chances are pretty good they do have some kind of output filter on it. But I have no idea, what kind of actual vertical resolution they have here. Let's see. Ramps still look like ramps, triangles still look like triangles. So I'd say it's fairly good resolution, but it's hard to say. But my point is that all DACs have a limit. And hell, this thing may actually adjust its voltage range. I didn't think of that because they may actually adjust their analog reference, as you lower your signal. So it's hard to say what kind of resolution this might actually be because there are all kinds of tricks they can play. And I'm saying in a normal situation though, where you have a fixed voltage output on a DAC, the vertical resolution actually does limit you at some point, especially if you have a high resolution signal. Eventually you run out of resolution. You got to start cutting corners somewhere, so things start to get choppy. But at any rate, that's just another little thing to look at. Even though this is a terrible example of that, because Analog Discoveries at least, covered those problems, so I can't really show you directly what I'm talking about. Because basically these signals, like even this, should look much more crude because we've got fewer bits of depth here. But again, the lowest apparently we can go is, man, I swear to God we were going lower than that in other videos. Oh, it's because I set my minimum. Okay, here, we can go lower. I thought that was kind of ridiculous. Yeah, so, here's 10 millivolts. Stupid limits, but like I said, noise starts getting in your way, at some point here, but, 10 millivolts still looks like a, 5 millivolts. Okay, there's an offset on this. What the hell's going on? Well, remember, this is the output of my amplifier. It's not the actual signal. I turned that off. Um, here's the signal here, the source signal. Let's see what that looks like. God damn it, stupid noise thing. So yeah, any rate, that's what the input signal looks like. But again, there's so much noise at this level, it's hard to say, but I mean, it does still look fairly well defined, surprisingly enough. Despite the noise, I mean, it actually still looks like a pretty smooth signal, right? So that's pretty, it's pretty interesting. So, like I said, they may be adjusting their analog reference, to match their signal resolution so they don't lose as much vertical resolution. But normally, again, if you don't have complicated circuitry like that, a DAC will have, you know, resolution limits on its, on what kind of how good your waveform looks, um, just due to vertical resolution problems, as well as frequency problems. So I don't know where the hell I'm at on this. Ugh, seriously? Okay, here we go. All right. So, but yeah, normally you'll have, resolution limits vertically. So if you had like a 6-bit DAC, at some point, even if you're not using all your resolution peak to peak, at some point you're going to be still running into having to change your waveform data, because you got fewer bits, vertical bits to work with because you're trying to make a lower voltage signal. So unless you can do tricks like Analog Discovery did and apparently vary their analog reference, so they can maintain the resolution better, then you're kind of screwed there too, as well as the frequency limits. Because like I said, right now, we got this set to, if you set it to like 200 samples, well, you got 200 samples per variability. That's why you're stuck at 2.5 kilohertz here. But you can generate a lot of oddball frequencies, and I'm not going to go into that because it's actually complicated. But you can do it on a spreadsheet. That's how I did. If you just think about it logically, because I've done it on a spreadsheet, but I can't really show you that because I don't know where it is. I mean, I think I know where it is, but you know, you wouldn't be able to see it very well in this particular camera mode I have right now. So, but at any rate, that pretty much covers that. So I just thought you might find that useful if you're thinking about, trying to understand DACs and what the real world ramifications of some of these issues are, because it's you really got to spend a lot of time kind of chewing on it, to make, to realize that, geez, my 1 mega sample DAC, you're going to be lucky if without a filter if you can generate, basic audio tones, you know, um, that don't look really crude. Because imagine what a real audio signal would look like. It's a lot more complex than this shit, and you got to have more, you want more resolution. So, but still, the filters coupled with the high resolution of a 16-bit DAC or whatnot still helps basically work through that, because it's got plenty of resolution to spare at audio frequencies, as you're seeing here, you know, because again, a lot of signals are going to look like that, right? But they're filtered over and smoothed out. But the key is they can have slightly different levels for each of these plateaus you see here. So that way they can recreate complex frequencies with it. So, songs, that kind of thing. So, but at any rate, that pretty much covers it for this video. Cheers.